Okay, so our next chapter is chapter 12, temperature and heat. Before we talk about equations and concepts, what is the meaning of temperature and heat? Uh, Temperature is a quantity that indicates how warm or how cold an object is relative to some standard. So, if some object has a higher number, then we know it. High value, high temperature, then we know it's hot. And if it is a very low number, then we know it's cold. And what is the heat? Heat is a form of energy which can transfer from one object to another object, mainly due to a temperature difference. So heat can transfer if there is a temperature difference from one place to another place. Okay, we use three common temperature scales: Celsius, Fahrenheit, and Kelvin. We will talk about Kelvin in next slide. So let's compare the Celsius scale and Fahrenheit scale. In this photograph, in this shows ice point. In Celsius scale, ice point is 0 degrees Celsius, and Fahrenheit scale it's 32 degree Fahrenheit, and the steam point for in Celsius scale is 100 Celsius. So in Celsius scale, between ice point to steam point, we have 100 units, and steam point in Fahrenheit scale is 212. So 212 minus 32 is 180 units. So 100 Celsius units is equal to 100 Fahrenheit units. So which is 1.8. So 1 Celsius is 59 Fahrenheit. So 59 is 1.8. So which is 180 divided by 100. So 1 Celsius is equal to 59 of Fahrenheit scale. So we can use this conversion to convert Celsius degree to Fahrenheit degrees or Fahrenheit to Celsius. Here, there's an example. You can convert Fahrenheit degrees to Celsius. So 98.6 Fahrenheit. Here, you have to subtract 32 degree Fahrenheit because degrees above ice point, because we know Celsius 0 degrees Celsius 0 is equal to 32 Fahrenheit. So you have to subtract 32, so you get 66.6 Fahrenheit, and then we know the relationship 959 Fahrenheit is equal to 1 Celsius. So if you use that relationship, you can get rid of Fahrenheit and convert 66.6 Fahrenheit to Celsius, which is 37 Celsius. Okay, so we talk about Fahrenheit and Celsius temperature scales, and the third one is Kelvin temperature scale. So here it shows the comparison of Kelvin scale versus Celsius scale. Here you see at ice point, Celsius is 0, we know that, and ice point in Kelvin scale is 273.15. We know if you use Fahrenheit scale, ice point is 32. So the steam point of Celsius scale is 100, and steam point for Kelvin scale is 373. The good news is it's very easy to compare Celsius to Kelvin because the difference between ice point and steam point is 100 units. And similarly here also the Kelvin scale also, the difference between ice point and steam point is only 100 degrees, 100 units. So each, in other words, each Celsius unit is easily convert to 1 Kelvin unit. So in other words, if we can convert any Celsius temperature to Kelvin scale temperature by adding 273.15, because that's the direct comparison. So for example, if you have 32 degrees Celsius, which is close to room temperature, in Fahrenheit scale, you can write 32 degrees Celsius plus you don't need Celsius because Kelvin scale you don't use degrees, so 273.15. So 305 Kelvin. So just adding 273.15 to Celsius scale measurement, you can convert to Kelvin. And for example, if you want to take the ice point Celsius in Kelvin, this number is 0. So you have 273.15. So 15, we can, simplicity, we can just consider 273. T equals 273 Kelvin is ice point. Okay, constant volume thermometer. Thermometer is a device we use to measure the temperature. So let's talk about how this works. I'm sure the right side you see a U-shaped tube filled with mercury, and over here you see a mercury filled tube and no air, which means here the pressure, I will write P1 is 0 because no evacuated space, which means there are no air molecules, therefore the pressure here is 0. So basically the pressure here, which is the pressure of the gas, is same as pressure here because we know the pressure at equal levels are same. So pressure, gas pressure is same as the pressure here, which is equal to pressure on top. If I write P2, we learn equation P2 is equal to P1 plus density, which is mercury, density of mercury, rho, and the height of the mercury column, height difference, h, and the gravity. So if the pressure 1 is 0, so it's evacuated. So the pressure to gas pressure is equal to rho hg. So put in this beaker filled with different temperature, we can measure the pressure. So the temperature basically proportional to the pressure. So if you increase the temperature of this bath, the pressure of these air molecules go up, and then the pressure too will go up. So you mean the height will go up. So how we measure the temperature? So I can write a equation. So temperature, if we want to measure something, that temperature is T, which is equal to, let me write P1. Let me write the equation first, and then we can go over the parameters. P1 minus P0, P100 minus P0. P0 is pressure at ice point. Pressure at ice point. So P100 is multiply by 100 C. So pressure at steam point, and the pressure one is the unknown pressure, or the pressure of the unknown temperature. So if you have something you want to measure the temperature, you just put it inside, and you can unknown, we don't know, so which is linked to this temperature. So if you know the pressure of the unknown liquid or unknown, and then you can use first you have to calibrate this thermometer with ice and steam, and then you can write down the pressure at the ice point and the steam point, and then and only thing is, when you have an unknown, you want to measure the temperature, you just put it inside this bulb, and then wait until the mercury column rises, and then measure the H, which is rho GH. So basically height difference at height when the pressure is at ice point, height of the mercury column when it's measuring the unknown substance, and height of the mercury column when you measure something at a steam point, and this is the same pressure when you measure something at ice point. So basically height difference multiplied by 100 Celsius, you can get a temperature in Celsius. And now once you get a Celsius temperature, you can add 273.15 to make it to Kelvin, or you can use the Celsius to Fahrenheit conversion to convert Celsius to Fahrenheit. Okay, so in this graph, we plot pressure versus temperature. So pressure is in vertical axis, and temperature is in the horizontal axis. And let's say we have some sort of a gas inside this bulb or container, and when you increase or decrease the temperature, we see a temperature and its corresponding pressure. So when you keep reduce the temperature, we know when you reduce the temperature, the motion of these molecules, gas molecules, reduced, and therefore its pressure reduced. So when you keep dropping the pressure temperature, its corresponding pressure also drop. Okay, so what will happen if you keep dropping the temperature? We know its pressure drops, and at one point when temperature reach to a certain value, its pressure is zero. So absolute pressure becomes zero. So that, pressure becomes zero. So that temperature corresponding to the pressure becomes zero. We call it absolute zero. So we can replace this gas with a different gas, and if you draw a similar graph, pressure versus temperature, let's say this one. So when you keep dropping that temperature, its pressure also, the slope is different, but it follows the similar trend. When you reduce the temperature, its pressure also drop. At one point, its pressure becomes zero. So here the interesting thing is the temperature at which the pressure becomes zero is same as the previous line, and if you use a different gas, another gas, and if you plot pressure versus temperature, again it meets at the same temperature. So that particular point, we call it absolute zero point in Celsius scale, which is negative 273.15. There are several different types of thermometers we use to measure the temperature. Here in this example, we use two different types of metal wires to make a thermometer. Here we use copper and constantine, which is a metal, which is a mixed metal of copper and nickel. So these two metals we connect with a spot weld, or we join these two metals together, and the other end of these two metals we use a resistance or voltage of this. Actually the voltage is proportional to the temperature. So each So the voltage we can measure, which is proportional to the temperature, and we use a meter, which has the conversion voltage to temperature, and we can directly measure the temperature from this meter. So we know gases, liquids, and solids expand when you increase the temperature. If you have a gas sample and if you increase the temperature, these atoms made out of this particular gas start vibrating, and therefore its volume increases. Similarly, if you take a piece of solid, and again they made out of atoms, and when you increase the temperature, the motion of these individual atoms increases, and therefore its length increases. So let's consider a rod, solid rod, which initial length is L naught, and if you increase the temperature of the rod by amount of delta T, and we can assume the increment of the length, initial length is L naught, and the increment is delta L. So here, if you have initial length L naught, and if you increase the temperature by delta T, it expands amount delta L. If you double the length, L is the initial length, if you double the length, and the increment also doubles, each L naught increase by delta L. So which means initial length and the increment is proportional. So if you increase the length, the amount it expand is also increases. So if L increases, initial length increases, the amount it expand also increases. So L naught initial length proportional to the amount of expansion. So if we reduce the initial length, it drops the expansion. So it has a direct relationship. Expansion is proportional to the initial length. In the previous page, we said initial length is proportional to the expansion, and also we know expansion is proportional to the temperature change. So if you increase the temperature, it will expand more. So this is proportional. So if you combine these two, we can write initial expansion, which is proportional to initial length and the temperature change. And we can get rid of this proportionality constant by adding a constant. And then we can write expansion, length expansion is equal to expansion coefficient alpha. This is expansion coefficient alpha, initial length times change of temperature. So this, for length, we can say this constant coefficient of linear expansion, because it's a length. So this is coefficient of linear expansion. The reason we call it linear expansion is if you consider a volume or area, we have another coefficients for area expansion and volume expansion. So if you get a length, then we can consider a coefficient as a linear expansion coefficient. So the unit of linear expansion coefficient is unit of length divided by unit of length divided by unit of times temperature, which is 1 over Celsius. So alpha is the coefficient delta L divided by L naught delta T. So unit of L is meters, unit of length is meters SI unit, and then unit is C. So 1 over Celsius, which is Celsius -1. Okay, so in this table shows a couple of common solids and liquids and linear expansion coefficient and volume expansion. So volume expansion, we use beta for volume expansion. So if you have a volume delta V, change of volume expansion, which is equal to beta initial volume V naught times delta T, temperature change. And if you have a length change is linear expansion coefficient times L naught initial length times delta t. So they are very similar equations. So basically coefficient can be linear volume or area, and then initial volume, initial length, it depending on which you're talking about. So it shows different expansion coefficients. Some material has high expansion coefficients, some of them are very small expansion coefficients. So in this example, it says concrete sidewalk is constructed between two buildings on a day when the temperature is 25 degrees Celsius. When the temperature rises to 38 degrees Celsius, the slabs expand, but there is no space between the two slabs, and therefore because of the expansion, it buckles like this. So if it is at 25 degrees Celsius, 25 degrees Celsius, it's flat. But when the temperature rises to 38, it expands because there's no gap, it buckles. So the question is, what is this length? So from the equation, we can calculate delta L. So once you calculate, delta L is initial length is 3.00000, and the expansion is delta L, which is 0.00047. So you can calculate this using expansion coefficient. Delta L is equal to alpha L naught delta T. So delta T is the time change, temperature change, which is 38 minus 25. Initial length, which is 3.000 0 meters, and then alpha is, you can look up the linear expansion coefficient of concrete, and then you can calculate. And once you have the expansion, you can calculate y. Y is, if you use the Pythagorean theorem, this is side, this is the hypotenuse, so 3.00047 square minus 3.00000 square, and if you take the square root, you will get the height it rises. From the table we showed for expansion coefficient, we know depending on the type of metal or solid or liquid, every metal or every material has a expansion coefficient. And if you make a like a strip or layer with two different metals glued together, like in this figure A, there are two types of metals here, is brass and steel. Brass is on your left side and steel on the right side. Those two metal strips glue together and make single strip. And if you heat up, we know one metal expand more than the other. So for example, brass has a little bit higher expansion coefficient compared to steel. Brass expansion coefficient is 57. It's a volume expansion, 10 to negative 6. Or steel 36, 10 to negative 6. So one has higher, so therefore this expand more. So if it expand more, it bend this way. If it cooled, then it's contract. So therefore it contract more, and therefore it bend opposite direction. So if you made out metals, strips with two different metals with different expansion coefficients, you can use these metal strips for various applications. So here's one application using a bimetallic strip in your coffee pot. So you can set the temperature using the knob, and then this knob, when you turn the knob, it connected to the electricity wall outlet and goes through the coil, and then it come back to the switch through a bimetallic strip. When the temperature goes up, we know uh, if it is a bimetallic strip, one side expand more and therefore it bend. If it bends, it open the circuit, which stop sending current to this coil, and it maintain when this strip cool down, it goes back and stick to the other side of the switch, and therefore it complete the switch again, then it start flowing electricity, and then it heat up again. So it can on and off in order to maintain a certain heat depending on the temperature you set on the knob. Here's another example. Let's assume there's a floor with certain tiles, 8 tiles, and you leave a hole uh, on the center, in the center. So when you heat up, we know it increases its length and side, basically the whole volume, and when you heat up, it expands, and therefore the 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 middle area doesn't have a tile also expand. So the amount of the expansion is same as the amount of the expansion of the other sides. So therefore it is sort of proportional. So in this example, there are three coaxial cylinders made out of three different metals. Brass, let me write the expansion coefficient. Brass, volume expansion is 57 times 10 to negative 6 per Celsius, and steel is 36 times 10 to negative 6, and lead is 87 times 10 to negative 6, 1 over Celsius. So the question is, when we heat up, the cylinder C falls off. So, and if cylinder C falls off, means the outer cylinder, means the outer cylinder expansion coefficient of the outer cylinder is higher than the inner cylinder. So if you compare the volume expansion coefficient of B and C, the outer material needs to be higher. So which means if the inner cylinder is made out of steel, the outer cylinder can be either brass or lead. So if the inner cylinder is steel, this can be brass or lead, because either case brass has a higher coefficient compared to steel, and also lead. So if the outer cylinder is lead, the middle cylinder should be steel. And and then in the second part it says cylinder A becomes tightly wedged to cylinder B. So which means the inner cylinder needs to have a higher coefficient compared to the outer cylinder. In this case, if you compare A and B, B needs to have a smaller coefficient compared to A. So if you have brass as inner cylinder, which is A, then the outer cylinder should be steel. So which means this A expand more than B, therefore A tight onto B. And similarly, A and B, if A made out of lead, which has a higher coefficient, then it expand more and then it tied onto B. So volume expansion is, this equation is very similar to the linear expansion. Delta L is linear expansion coefficient, initial length times temperature change. Volume change, volume expansion coefficient, initial volume and temperature change. Okay, so in this example, we know we have a coolant reservoir made out of plastic and then the radiator made out of brass. Let's see, copper, sorry. It's made out of copper. And then it has coolant. Inside the radiator has coolant and then copper radiator. And the question is, at normal temperature, it is 6 degrees Celsius, and when it heat up, the radiator and the coolant becomes 92. So there's a temperature change 96 to 92. And we know copper and coolant volume expansion, and then we can check how much coolant expand more compared to the radiator. So we can check delta V, volume expansion of radiator, and also we can check volume expansion of coolant. And if you can use the formula beta V naught of the radiator, initial volume of the radiator, and temperature change 92 minus 6. This is the copper volume expansion coefficient, and similarly you can use this coolant volume expansion coefficient, volume of coolant, and the temperature change 6 to 92. And the difference, delta V coolant minus delta V radiator, is the amount of coolant expand and it flow into this reservoir. Here it shows the volume expansion of coolant coefficient, volume expansion coefficient, and the initial volume and the temperature 92 minus 6, which goes to here, and 0.53 quarts. And then the volume expansion of the radiator is the copper expansion coefficient, volume, and the temperature change. So if you subtract one from the other, so 0.46 is the difference. Coolant leak into the reservoir. We know density is equal to mass over volume. If volume increases, so your density is mass over volume. When volume increases, density decreases. When volume decreases, density increases. So we know if something, object or any material heat up, its volume normally increases, which means its density decreases. So for example, if this is a temperature scale, so if you increase the temperature in this equation, volume increase, therefore density decrease. So if you have density versus volume, if you increase the temperature, you see density decreases. So if you decrease the temperature, volume decreases, and therefore density increases. For example, if you take water, it has a very strange behavior. It follows the same trend, but up to 4 degrees Celsius. So after 4 degrees Celsius, when it cools more, its density decreases. So let me take an example. Let's take a like a pond or something filled with water. So during summer period, let's say 32 degrees Celsius. So it's hot summer time, 32 degrees, and when winter comes, temperatures start falling down 20, 10, and eventually it reached to like 4 degrees Celsius. So what happens is when temperature drops, usually the surface temperature drops quicker. So when the temperature drops, volume drops, and then density increases. When the density increases, the water goes to bottom, and when temperature keep falling below 0 degrees, top of the pond has ice, 0 degrees Celsius, and this ice layer over here like 4 degrees Celsius, because when the temperature keep going down, density goes down, and then the water on the surface goes down, and over down bottom goes up because it has a higher density. And when the temperature reach to 0, we have a thick ice layer which act as an insulation, and therefore it doesn't cool the water at 4 degrees centigrade even lower. So therefore, on top has ice layer, and on bottom it has a 4 degree Celsius water, which maintain that temperature throughout the winter, because we have heat from the floor ground, and therefore it maintains this temperature. When we talk about today's topic chapter, we briefly explain the temperature and heat. We mentioned that heat is a form of energy which transfer from due to the temperature change. So definition of heat is it's an energy that flows from high temperature object to a lower temperature object. If you holding a hot object, then heat transfer, because it's warmer than your hand, therefore it transfer heat in this direction. And if you touching a cold object like a cold drink or something, drink is colder than your hand temperature, therefore heat transfer from your hand to the cup. And SI unit of heat, because it's a form of energy, therefore joule J. SI unit is joule J. Okay, so heat supplied or removed in change in the temperature of a substrate is given by this equation. So heat, we use Q for heat, M for mass, delta T is temperature change, and C is a constant, we call it specific heat capacity. It depends on the nature of the material. So for example, oil and water. If you have a hot oil bath, it takes long time to cool down to a room temperature. If you compare with the 100 degree Celsius water container and an oil container takes long time to cool down to room temperature, 100 degree to let's say 30 degrees Celsius, room temperature close to. So it takes long time to cool down to room temperature at 100 degrees Celsius oil, because oil has a higher specific heat capacity. In next few slides, I will show you the specific heat capacity of some materials, and depending on this value, we need large amount of heat or small amount of heat to increase the temperature or change its temperature from initial value to a certain value. And also it depends on the amount of heat required to change the temperature, also depending on the mass. If you have a small cup with a little water, and if you have a large cup with lot of water, if you want to increase the temperature to 100 degree, this definitely need large amount of heat to increase because it has a higher mass compared to this. So this table shows a specific heat capacity of some solids and liquid. So for example, specific heat capacity of water is 4000. Specific heat capacity of aluminum is like 900. So human body is like 3500. So it takes long time. If this heat capacity is large, means it takes long time to change the temperature by supplying heat, so or cool down. So if you have something made out of aluminum, it's easy to heat up, and also it is easy to cool down because it has a smaller heat capacity. So some like water, it takes more heat to change its temperature because it has a higher heating capacity. Okay, so in this example, it says 65 kilogram jogger can generate this amount of heat, and this heat is removed from the body by variety of means, including own temperature regulating mechanism. If the heat were not removed, if Q not removed, your body temperature needs to go up. And the question is, what is the temperature increment? So you can solve for delta T, which is Q over mass divided by specific heat capacity of body, which is 3500. So heat generated is 8 times 10 to 5 joule divided by mass of the jogger and the specific heat. And when you solve this, you will get 3.5 degrees Celsius. So your body temperature will go up by this amount if the heat your body generate didn't remove. So colorimetry is an area or field of study we to identify heat change or change of state from like solid to liquid or solid to gas phase. Colorimetry is a branch of science we use to study heat change or phase change of materials. So in order to do this kind of experiments or studies, we need a colorimeter cup. Colorimeter is it can be like a thermal flask, or like even styrofoam cup can consider as a colorimeter cup because it can retain heat. So in this example, you see a colorimeter cup. Basically, it has like two walls. So one cup inside another cup. So the gap between the cups considered as a good insulation layer, and it has a lid. And if you put anything inside to check the heat change, you can study using that heat. We learned an equation. Heat is in mass, specific heat capacity, and temperature change. We can easily measure the temperature change using a thermometer, and we can measure the mass, and also We can look up the specific heat capacity from tables, heat capacity, and then we can measure the temperature, heat change. So if you do a experiment inside a container or colorimeter, we know heat change, there is no heat loss to atmosphere. All the heat loss from one object can goes to the other object. So I will give you an example in the next slide. Okay, let me give you an example for you to understand this section better, because this section, uh, the lab I'm going to assign is related to this section, and if you understand what I'm going to explain in the rest of this slide will help you to complete the lab today. So, so in this beaker, let's say it has water, and mass of the water, let's say like 120 grams, and the temperature of the water, let's say 30 degrees Celsius, and also let's say specific heat capacity C, let's say water, specific heat capacity of water is 207 times 10 to negative 6. You can look up these numbers, and let's say we have a piece of lead, yeah, piece of lead, and mass of the lead, let's say 100 grams. Okay, I'm making up these numbers. Specific heat capacity you can look up. Lead, which is 87 times 10 to negative 6, and let's say the temperature of the lead at a higher temperature, let's say 150 degrees Celsius. So water is in the lower temperature and compared to the piece of lead. And now let's say I drop this into the water, the piece of lead into the water, and you know lead is at higher temperature, therefore it releases heat into the water, because we know heat transfer from hot object to cold object. So in this case it's lead to water, and let's say everything we did inside a colorimeter, which means there is no heat loss to the surrounding atmosphere. So in other words, we know Q is the heat. We can use the same equation for heat gain and heat loss, because lead going to lose heat because it needs to transfer heat to water. On the other hand, water gain heat, or because it gain heat because lead is releasing the amount lead release onto the water, which means the temperature of water needs to go up because it gain heat from lead, and also the initial temperature of the lead needs to go down, and at the end those lead and water come to some sort of a certain temperature. Let's say we don't know that temperature, both lead and water come to a equilibrium temperature, let's say T. We're going to find out once you add this, and if you wait long enough, it reach both lead and water reach to a certain constant temperature, and we can use this heat equation, mass, specific heat capacity, and temperature change uh, to calculate. Let me use two different colors. Let me use dark blue for lead, and lead, we know heat loss, Q equals mass is 100. I'm not going to convert to kilograms right now. Let's leave it as it is. And specific heat capacity 87 times 10 to negative 6. Again, keep I'm not going to write the units. It's 1 over Celsius, but keep ion temperature units. You know, if you have Celsius or Kelvin, you have to convert to same units, because otherwise when you do the final calculations, your final answer is not correct if you end up with two different units for temperature. And we know that delta T is the temperature change. So it is 150 initial temperature, and the final temperature of lead we don't know. We say, let's say T. So heat loss Q is equal to 100 grams times 87 times 10 to negative 6 times temperature change 150 minus T. And I can write the similar equation for water. Let me use a lighter color for heat, water, heat gain. So which is again Q, mass of water, which is 120 times specific heat capacity 207 times 10 to negative 6, and then temperature change. Initial temperature is 30 and final temperature is T, because final temperature needs to be higher than initial temperature of water because it gain heat. So T 30. So this is Q for heat gain, water, and heat loss, lead. Okay, now you can write heat gain by water is equal to heat loss from lead. So heat gain by water is mass, specific heat capacity 207 times 10 to negative 6, and the temperature change T minus 30. So these two are equal because there is no heat loss to the surrounding, because you've done this test inside a calorimeter. So therefore there is no heat loss to surrounding, or there is no other way of losing heat. So, and heat gained by water is equal to heat loss from lead, which is equal to 100 mass of lead times specific heat capacity 87 times 10 to negative 6, and initial temperature is 150 of lead, and then it reached to a temperature T where we're going to calculate. So when you simplify this equation, you will get 61 degrees Celsius. So that's the temperature of the final temperature of the water and the lead. Reach after the equilibrium. You know, it takes few minutes to reach to a certain temperature, and you can do this heat transfer from one to the other, and you can calculate the temperature. Okay, the example I gave you in the previous slide is the very basic, simplest example I can think of, and here's a little bit difficult example. You know, it's similar, but let's read the problem. The calorimeter is made out of 0.15 kilogram of aluminum container, and it has 0.2 kilogram of water. Initially, the water and the calorimeter has the same temperature, 18 degrees Celsius. And then you add a 0.040 kilogram mass, which has a higher temperature, into the water. So when the system come to a thermal equilibrium, the temperature of the water, the cup and the material is 22 degrees. So you add 97 degree unknown material into water, and as in the previous case, you see the temperature of the water rise because temperature at a lower temperature. So here you have to ignore the small amount of heat gained by the thermometer. So you have a thermometer inside, so which means it gain heat, but you have asked to ignore, because then you have to consider the mass of the thermometer, specific heat capacity, if you want to do the calculation. But if it's a very small amount, you can ignore that. And the question is, what is the specific heat capacity of the unknown material? So when you do this, we know the hottest object is the unknown material. So heat loss from unknown material is equal to heat gain by water plus heat gain by the colorimeter or the colorimeter cup. So if you know that this is made out of aluminum, if you know the mass of the cup, specific heat capacity of the cup, initial temperature and final temperature of the cup, you can calculate delta T, and you can calculate heat gained by the cup and also heat gained by the water. If you know the mass of the water, specific heat capacity and the temperature change, you can calculate heat gain. And then heat loss from the unknown is equal to mass of the unknown. Specific heat capacity is not given, which we're going to calculate, and then the initial temperature and final temperature, which are given. So therefore you can calculate the specific heat capacity of the unknown. This is the only variable you need to calculate in this equation. So the example I gave you, I didn't include this part, so I just assume the water gain by heat gain by the water and heat loss from the lead is equal. Okay, here's the equation. Heat gain by aluminum and heat gain by water and heat loss by unknown, and then you have to solve for C, which is the specific heat capacity of unknown, and it says 1300 joules per kilogram per